Okay, so I don't know if that's the right, really the right expression, but I would like to thank you for being here and attending this this presentation. And before I forget, I would like to thank my supervisors, Björn, Jose, and Alberto, and Johan, who is the opponent today. The title of my midterm presentation is called Thermal Response of Borehole Heat Exchangers, Modeling and Experimental Analysis. This is the outline of the presentation. First, I will give a little background and global context. Then I will talk about thermal response tests, and in particular about how noise in thermal response tests can influence the parameter estimation. In the next part, we'll talk about deep boreholes, some preliminary economic analysis, and some preliminary results from field tests. In part 4, we'll talk about lab scale experiment, and in particular how to design borehole on scale so that you can make experiment in the lab. In part 5, I will quickly mention high temperature borehole thermal energy storage, performance indicator, and case study. And the last part, I will talk about field work. So now to the first part, global context and introduction. What we see in this picture is greenhouse gas emission in 2016 divided by per sector, and hand use activity and the type of emitted gases. We don't need to look at it into details. I think what is important is that or what I want you to take away from this is that buildings represent quite a large part in this greenhouse gas emissions, a large share in this buildings and also industry. And the reason for which I mentioned those two sectors is that ground source heat pump, I think, have a potential to help reduce greenhouse gas emission in those two sectors. This is what it looks like if you look at the final energy use worldwide. You see it's divided fairly between 3 different sectors: residential and services, transport, and industry. And in the residential and services, ground source heat pump represent less than 1%. But as we said, they have a good potential, and I will get back to that. But first, I would like to just quickly introduce what I mean with ground source heat pump. So when we talk about ground source heat pump system, usually we think about 3 main components. So of course, a heat pump, a building or some hand use application, and a borehole or underground heat exchanger. In this presentation, I will only mention vertical closed loop systems. And there are, of course, many other components that are of interest, but I will not mention right now. Of course, you could have 1 or several boreholes, in which case you could talk about the borehole thermal energy storage. In this figure, what we see is the minimum seasonal performance factor that you should have in each European country in order to lead greenhouse gas emission with natural gas boiler as a reference. And the order have placed the order have placed a regular SPF at about 3.5. I think that maybe it should be a little bit lower, but still we see that there is some good potential in most European countries, and especially in the countries in which the carbon intensity of the electricity production is low. For instance, in Sweden. Okay, but you of course have some challenges with ground source heat pump systems, and here I list some of them, and I try to outline how the different papers and reports well, talk about this issue or deal with some of these issues, I should say. So for instance, with TRT, we investigate how to estimate unknown thermal parameters underground, and this has in turn an impact on investment cost, or rather how to make the best of your investment. In the report about the borehole, we cover a wider spectrum of challenges. In the lab scale part, well, the final aim is to have a test bench that you can use for model validation, which in turn also will might impact your investment cost. And in the high temperature borehole thermal energy storage, we talk about performance indicators and system integration. Okay, so now to the second part, thermal response test. So thermal response tests are tests that are used to understand what is underground, or more particularly, what are the thermal properties that we have underground. And these are very important parameters when designing ground source heat pump systems. And the test, well, this is a typical setup for thermal response test. And the test consists in injecting heat in the ground through fluid circulating in the borehole heat exchanger, and monitoring how the fluid temperature changes over time. So this is what the average fluid temperature could look like under a thermal response test, which is fairly long. It lasts for several days. And once you obtain this experimental data, what you try to do is that you try to fit a model that has the parameter that you want to obtain as parameter inside the model, and the parameter that, or to find the parameters, you choose the best fit between your experimental data and your model. So you adjust the parameters so that the model fits the experimental data. And when I say parameter, what I mean in most cases is that we want to find out the thermal conductivity of the ground and the borehole thermal resistance, both as effective values, so kind of lumped values. In the first paper, which is called Thermal Response Test, a biased estimation procedure question mark, we investigate how measurement noise is affecting the parameter estimation. Then in particular, can noise on the input power that you inject in your borehole lead to a biased estimation, because there are some results in other fields that suggest that this could be the case, namely system identification. And if we take a step back and think about why we want to do that, well, I mean, if we have actually an error in the parameter estimation of CRT, this means that you have a wrong background information for your design, and you could have some impact on your, well, design and cost of your system. And as far as I know, there is no systematic investigation of measurement noise, and especially this potential bias in the estimation. So this is another representation of thermal response test, where you see we have the heat rate per meter, so the heat we inject inside the borehole. And this is our system, so the borehole heat exchanger and the ground. And here we have our temperature change. So when we inject heat into the system, we obtain some temperature change over time. And these parameters are the true, these variables, I should say, are the true variables. So what happens in reality. But we can only have a corrupted idea of what these parameters actually are, because when we perform measurement, or our measurement always have some noise. And well, in the system, this theta variable represents the parameter of your model, I should say. So thinking about this framework and thinking also about minimizing the error between your model and your experimental data, what we try to do when we analyze thermal response tests is that we want to minimize cost function, which is just the sum of squared errors between your model and your experimental data. So this is just what we see here. And of course, in this estimation, we use the measurements that we have because we don't have access to the true value of the variables. Since you, well, before I show that, I think I should say that since we have noise in those variables, the cost function in itself become a random variable as well. And we can look at what happens when we take into account the noise and take, for instance, the expectation. So this is what you would expect to obtain if you would do a really large or namely infinite amount of tests and look at how the noise influence this cost function, because it will influence the parameter estimation. And in the paper, we make an analytical derivation of this, but I'm not going to go through this. I just want to say that this is what we truly want to minimize, the true temperature change and the true model, you could say, or not the true model, but the true heat rate and our parameterized model. And you see that this is the variance of the noise on the temperature change, and it's not changing the position of the minimum of the cost function. So that's not so problematic, you could say. But if you look at this term, we see that it depends on the parameter themselves. So this will create sort of like a penalty in the cost function, and it will move the position of the minimum. So the parameters that you obtain will not correspond to the true parameters. So there is, analytically, we show that there is a bias in the estimation. But now the question is, well, how large is this? How large is this bias? Maybe it's small and we don't have to care about it. And also, since the cost function is a random variable, we have to understand how the stochastics of the cost function influence the parameter estimation, especially because only one TRT is performed in most cases. So if you would perform many tests, then you could average the results of those tests and remove the stochastic nature. But since we only perform one test, this stochastic component might be important. Okay. In order to do this, we did a Monte Carlo analysis with different noise variants and different parameter values. So this gives us a certain number of cases, and for each of those cases, we investigate 4 different heat rate profiles that you see here. And then for each of those subcases, we perform 500 TRT simulation, which in total give about 84,000 TRT simulations. And ILS, the infinite line source model, is used for generation and interpretation. So we remove any potential model error in the interpretation. This is what the results will look like. This is the parameter space, the thermal conductivity, and the borehole thermal resistance. And here in color, you see the cost function. And here, for instance, this is where the minimum is, and all the estimates are in circle, in white circle. So they're all centered here because in this specific case, we don't have noise. On the left, I will show the projection of the cost function along the true value of the borehole thermal resistance. And you also see a histogram of the different estimates for the 500 realization, and the same thing along the other direction. So in this specific case, there is no spread of the estimates. They're all centered at the true value because there is no noise. And here I will remind the conditions under which these simulations are performed. So what happens if we start adding noise? For instance, on the temperature change. What we see is that in average, this is the average of the estimates, and it's equal to the true value, so that's good. But still, for each TRT, we might be a bit off because there is this stochastic nature. So each of those results here, or each of those estimates correspond to one TRT only. And now what happens if we also add noise on the input rate? Or before I just want to remind you that I said before that the noise on the temperature change is not so much of a problem because it doesn't change the position of the minimum, and this is what we see here. What happens if we add noise on the input rate? Input heat rate. Well, it depends. There is a big dependency on the value of the thermal conductivity. So here, for instance, there is no spread of the estimates, and the average of the estimates, or almost no spread, and the average of the estimates is almost equal to the true value. So the bias that we talked about before is not big. But if we go over to larger value of thermal conductivity, then we see both that the bias, so the difference between the average of the estimates and the true value, becomes larger, and also the spread becomes larger. So this might be problematic because, as I said, only one TRT is performed, and you might get some results that are far off the value that you actually want to estimate. Another thing that we did investigate in this paper was how the bias was influenced. Bias and standard deviation were influenced by the sampling frequency. How many samples do you take during your test? And here what you see is the standard deviation for different sampling frequency, and also versus the noise variance on the input rate. So the first thing we can notice is that when the variance is larger, then the standard deviation is larger. And when the sampling frequency is higher, so we have more points, then we reduce the standard deviation of the estimates. If we look at the bias, we see that it's always negative, first of all. And the sampling frequency doesn't have much influence on the bias. But there is a clear trend of with the noise variance, and this is not weird if we remember the expression that I showed before. This is the same thing, but with the noise on the temperature change. And I said that the noise variance on the temperature change doesn't affect the bias, but it looks here like we have a trend, which is simply due to those points having being corresponding to some variance on the input heat rate as well. But when we don't have any noise on the input heat rate, then the bias is 0 for even when we have noise on this temperature change over time. Some limitation of this study: the noise are considered independently and identically distributed, so there are no correlation and no cross correlation either. And the numerical results, they're specific to the tested conditions. So although we tested different conditions, it should be understood how this can be extrapolated for all type of conditions. And in conclusion, well, the parameter estimation is biased because of this term that we talked about before. And the bias and standard deviation as high as 6 to 7% are observed. And for larger thermal conductivity, then both of those values will be larger. But a good strategy maybe to avoid this issue is to have a higher heat rate per meter. It reduces both the bias and standard deviation. The larger sampling frequency will help reduce the standard deviation. And I think, so as final conclusion, I think even though this problem might not always occur, I think people should be aware of it when performing TRT analysis. So now to the second paper, in which we also investigate noise, but the question is a bit different, namely how can several models compare to each other when determining the thermal parameters, and especially how is the ILS, so the first order approximation of the ILS be used when you have some drifting heat rate, which I will explain in a second. And the reason that for which we want to investigate this is, well, the same as before. If you have some errors in the parameter estimation, you impact your cost and or your design, and in turn the cost. And also ILS is used in most TRT analysis. So what we did here was that we took two different types of heat rate per meter, either a perfect one that is perfectly constant, or some that show small variation over time. And this is what we call a drifting heat rate. So there is a small correlation in time. And then we use a composite model to generate the thermal response with some parameters and those two heat rate profiles. And that added some noise or not on the input rate, and also the temperature change over time. And then we use a different type of model to do the interpretation of the TRT. And this is what we obtain. So here you see the position of the parameter estimation in the cost function domain, or the parameter space domain. So when we have perfect heat rate profile with no noise, then we still have a difference, which is quite similar for, well, something I didn't say is that we use two types of interpretation model: the ILS first order approximation, in which we use a linear regression in logarithmic time, and a time superposed ILS, in which we use an optimization to find the true parameter, the optimal parameters. And what we observed here was that there was a model error, or there was an error due to difference in model used, which was about 7%. And if we change to a drifting heat rate, what happens? Well, for the time superposed ILS, which can account for this variation, there is no difference at all. But for the regression, the first order approximation, then the difference becomes much larger, and here we have a 20% difference. And this variation is not big, so it's within the Ashray criterion for TRT, which specifies that the deviation of the power should be within 1.5% of the average power injected. And this heat rate respects this condition, but I think this criteria may be, or we should have another indicator, let's say, for when we can apply the first order ILS approximation, because what is important here is that there is some correlation in time, although the variation is small. When we had noise, it doesn't change much. In this specific case, we observed a higher deviation for the first order ILS approximation. And if we take a perfect heat rate profile again and had some measurement noise on it, then the ILS first order approximation still performs well, because it can deal with random noise over the heat rate profile. So some limitation is that the results are specific to the two models used for generation and interpretation. And although we have nodes that are random, we only perform one realization per case. And in conclusion, I think what we should retain that the ILS first order approximation can perform poorly for drifting heat rate, so we should be aware of that. We noticed a model error of about 7%, so we should understand how does that affect parameter estimation in TRT as a whole, or what models should we use for parameter estimation? And then that the Ashray criterion is not sufficient to understand when the ILS regression can be applied. And if you have to choose between the two ILS methods, I should say, I think you should use time superposed, but also with other models, because we saw there was this model error of 7%. This is also a suggestion of the Ashray criteria for TRT, guidelines, I should say. In this third paper, we talk about the convergence algorithm for TRT. So how do you minimize your cost function? And the goal, rather than the question, was that we wanted to have an algorithm that always converges and always converges to the same values. Of course, we want to avoid incorrect convergence. And parameter estimation should be fast, especially if you have to use several models, as I was suggesting before. So this is the objective function. This is exactly the same thing that we saw before. So it's the sum of squared error between the model and the data. And I'm going to go rather quickly on that, but this is what the optimization algorithm looks like. And we did some analytical derivation of this Hessian matrix, which is just the second order derivative of the cost function. But since we only have two parameters here, this matrix can be readily inversed. So we skip the computational burden of inversing this matrix. And if we look at the robustness and consistency, I mean, what we did was we tried several different initial guess and look at if the algorithm was always converging to the same value, and this is what you see here. And compared to another more heuristic and robust algorithm, this method was a little bit faster. So the limitation is that the algorithm is specific to the time superposed ILS, and it's also, the results are also implementation dependent. So maybe using another software, we'll find different results, and also the implementation of the algorithm themselves. But over 99 TRT analysis, the algorithm always converged and to the same values. And it was faster than the Nelder-Mead algorithm for the implementation used. Okay, over now to deep boreholes. All this section is based on one report, a project report, in which the main question was, are deep borehole techno-economically interesting for ground source heat pump? And the reason for which this question was asked was that we saw more and more deep boreholes being drilled in Sweden, at least, and there's a lack of space in tightly built areas for which deep borehole are one of the solutions. This is the deepest borehole per year and the average depth over time since 1990. And especially in recent years, you see that there's been an increase in the deepest borehole. And I don't know if there are any deeper borehole as of today, but it wouldn't surprise me. As I said, one of the reasons to have deep borehole is that you may have limited space for drilling, and you still require some borehole length. So what you could do is that you could drill deeper to match the specification of your system design. Here are some specific advantages and drawbacks with the borehole. So for instance, thermal shunt, the heat transfer between downward and upward going pipe inside the borehole. Also, the investment cost will be larger and there's maybe higher risk when drilling deeper. At the same time, you reach higher temperatures, so this could lead to higher COPs. But pipes are longer inside the borehole, so the pumping power might become important. So these are elements that can make the balance tip, especially because they influence operational costs. What we need to understand to have a picture of investment cost was to ask Swedish drillers through a survey, and this is what the answer looks like. So what we see is the drilling price per meter for different depth. And we don't have to look at the equation specifically, but what we should notice is that the price increases non-linearly with depth. Also, there is a high spread in the answers, which characterize maybe some kind of uncertainty. And based on this survey, we did two examples of total price for borehole ground source heat pump installation for single borehole and 5 boreholes for different depths. And you see the uncertainty bounds that I showed before. Below here, you see the price model that was used for drilling. Another thing that we did was to do a test in a 800-meter deep borehole in Askøy, Norway. And this borehole had a coaxial heat exchanger, so a pipe-in-pipe heat exchanger, in opposition to the more usual U-pipe heat exchanger used in most borehole heat exchanger today. And this is how the fluid circulates inside the coaxial heat exchanger from the annulus, in that case, to the center pipe. And in this specific case, we use, in addition to the more common instrumentation, we use a distributed temperature sensing unit using fiber optic cables and a laser to measure temperature along the depth. This is what we obtain when measuring the pressure drop for different flow rates inside the coaxial borehole heat exchanger in comparison with U-pipes, so more common type of heat exchanger. And you see that we have a lower pressure drop than U-pipes for the same depth, but even for smaller borehole depth. So pressure drop might not always be an issue with deep boreholes. This is just an example of the type of information you obtain with the fiber distributed temperature sensing. And here what I show is that I show a period in which we perform 3 different heat extraction tests under different period. And these are some example of temperature profiles that we obtain. So on the left, you see the undisturbed profile, what the temperature looks like before you start performing your test. Under circulation, so when the temperature sort of equalizes inside the borehole. Here is after 200 hours of heat extraction. And this is under the recovery, so 100 hours after the test was stopped. And we also did some heat injection tests, and you see that the profiles look quite different. And here, especially, there is something that you may notice, which is that the temperature at the bottom are not corresponding to each other. And I think there is some more effort to do in calibration and uncertainty of this measuring equipment. So what I show is raw data. But based on those profile, anyway, something we could look at or investigate was what I call heat flux inversion, or something we could notice, I should say, rather. Heat flux inversion. So what you see here is the heat flux for different sections over along the borehole depth. Qg is the amount of heat extracted from the ground, and this Q12 is the thermal shunt between the two pipes. And something we noticed, which is more visible here, is that at the top of the borehole, even though we are doing extraction, at the top of the borehole, we are injecting heat inside the ground. And this is, well, I think because of the geothermal gradient that we have inside the borehole. So I think it's an interesting phenomena that could deserve being investigated further. And using, again, the distributed temperature profiles, what we could calculate was how the thermal shunt, so the heat transfer between the center pipe and the annulus that you see here, how large was this in comparison to the total amount of extracted heat? You would like this ratio to be 0 because you don't want any of this. You don't want to lose heat. You don't want your fluid to lose heat on the way up. But here we see that it's, for all the tested flow rates, we see that it's always at least as high as the total amount of extracted heat. And we have a decreasing trend with increasing flow rate. So this might, we haven't really quantified it yet, but this might have an influence into the thermal performance of the deep borehole heat exchanger. Okay, some limitation of the study. Well, we only looked at investment cost and not running cost. I talked about the uncertainty of the distributed temperature sensing measurement that should be further investigated. The pressure drop that I showed is only valid for this specific site, so it should be understood how other sites perform and how can we maybe have a more general idea about coaxial pressure drop in coaxial heat exchangers. The survey is limited to Sweden and it's a rather small sample size. I think more work is needed to, as a conclusion, I think more work is needed to assess the techno-economics of deep borehole, especially as regard to running costs, as I said. There is this feature of the geothermal gradient. Here I write that it might affect the boundary condition of the borehole wall. So this might have an impact on modeling. And we saw that the thermal shunt, so the heat loss from the center pipe to the annulus was large in the borehole. And this is not surprising, but we were able to give some quantification. And pressure drop is not necessarily an issue, in at least with coaxial borehole heat exchangers. Okay, now part 4, which is about lab scale experiments. And this part is based on 2 papers in which we discuss design methodology for this type of borehole inside the lab, you could say. And the question, well, the questions that we try to investigate in these papers, well, first, how can we make sure that the result we obtain with such a lab scale test bench can be upscaled and applied to real size boreholes? And also, what size should I have for this lab scale test units? And the reason for which we want to do that is that there is a need for validation of heat transfer model underground. I wrote in a controlled environment, and I will explain that in a second. And again, the models are used for design of ground source heat pumps. So having accurate model will impact both the design and also the way the cost effectiveness of the system. And instead of performing or instead of validating with a lab equipment, you could think about monitoring a real system and looking at how it performs over time. But there are some, I think, some issues with that, namely that we're not sure about the thermal parameters that we have on the ground. We might have different geological layers. The boreholes might not be exactly as you think they look like. So, for instance, they might be inclined and you might have some groundwater flow on the ground. So I think there could be a lot of uncontrolled conditions which are hard to assess. And not least, the time scale is long. So a ground source heat pump system, at least, well, the heat exchange in underground will be transient for the whole lifetime of the system, which is about 20 to 25 years. So these would be, if you want to validate your model on the long term, you would require a lot of time. But just looking at the Fourier number here, we can understand why the benefit of downscaling, because when you reduce the size of your system, then your time is reduced by the square of this reduction, you could say. So you will have tests that are much shorter. So you're able to test 20, 25 years in maybe a week. This is just a picture of what the test bench was conceptualized, I should say, with the different design parameters. I'm not going to go into details, but it's well, it's a couple of things to think about, I guess. But back to the first question. So how can we make sure that the result we obtain in the lab scale experiment can be upscaled to the real scale borehole fields? And what we did in the paper is that we took the two heat equations and their boundary condition and did basically some change of variables. And what we obtained was that all of these dimensionless numbers should be conserved. And maybe it's not surprising. So the Fourier number is the dimensionless time, you could say. This Biot number is, well, I think also a dimensionless number, but it represents the convection coefficient that you have at the top of your borehole. TRF stands for thermal response function. So this is the dimensionless response at the borehole wall. So how the temperature will change over time at the borehole wall in dimensionless form. And this is the dimensionless geothermal gradient. And I think those two parameters are most of interest. The first one, because when you downscale this, when you reduce your H, which is the borehole length, by the way, you will have a higher requirement on your convection coefficient. And since this is reduced quite a lot, you have to be careful about what the requirements becomes here. We'll talk about that later on. But the second one is interesting because this is what we want to test. So it's sort of a nice thing that this becomes as a requirements that it should be conserved. So now we have the analytical requirements, but still we need to understand well what size should my borehole storage on scale have, how large should it be, and so on. And in order to do that, we made some we proposed a design methodology and used some numerical simulation in order to understand how, specifically how the boundaries affect your thermal response. And this is what we found. So what you see here is the difference in thermal response at the borehole wall for models of different size. So what you see here is the ratio between the total height of the model and the radius of the model, and the borehole length inside the lab scale model. And this is the difference, as I said, in thermal response between each size and a reference model, which is very large. So there is a very small influence of the boundaries. And the requirement here was that the difference should be lower than the extended uncertainty of the temperature change measurement at the borehole wall. And so this is the size that was retained. So the lab scale experimental test bench should be twice as high and twice as wide, you could say, or with a radius twice as large as the borehole depth. And then looking at how the scaling, so how the space scaling influence different practical parameters. So this beta here is how much we reduce the space from the real scale to the downscale. What you see, for instance, is that the more you reduce your scale, the more your test duration decreases. Also, the mass of your system decreases, which maybe makes sense, and the height of your system, or the size, I should say, height and radius also decreases. At the same time, if you increase this reduction in scale, you will obtain or you will have some high requirements on the borehole radius that you should have, because in real scale, the borehole radius is very small in comparison to the total borehole depth. This might be problematic because these are extremely small dimensions. So there is this compromise to do. And also for the convection coefficient, as we saw, if you reduce the scale a lot, then the requirements on the convection coefficient at the top of your borehole model will be high. Mainly looking at the test duration and the mass, we chose a geometrical scale factor of about 600, which means that if you have a 300-meter borehole, you will emulate that in the lab with a 50-centimeter deep borehole. But these present some challenges with the borehole radius and the convection coefficient. So we investigated these two components a little bit further. So what you see here is the thermal response function for different borehole radii and different spacing between the boreholes. I didn't say it, but the borehole configuration that we studied was a 4x4 borehole field. So what we see is that if you multiply your borehole radius by 5 or 10, then you will have quite an important impact on your thermal response function. So since this is a challenge in the experimental implementation, you should understand at least, well, how much is this difference, and can I try to correct it? And there was a correction that was proposed earlier by Claesson based on steady state conduction between the two radius. And here you see what happens when you apply the correction to those curves. So still, I think there is some notable difference at the end and also at the beginning, which is not so surprising, but this just means that we have to find maybe a better way to correct the results if we perform them with a borehole radius that is larger than the analytical requirements. Now to the convection coefficient at the top of the borehole. Again, we see thermal response for different spacing between the boreholes, and then different Biot number, which represent the convection coefficient at the top of your borehole, but it's not it doesn't represent the same value in the real case than in the lab case. So for instance, about number of 857 represent a convection coefficient of 10 in the real scale, but of 5,000 in the lab scale. So this is really challenging to reproduce experimentally. What we see is that, what we see here maybe is that when the bout number tend to infinity, so this is a constant temperature boundary condition, you almost have no difference with a convection of 10 watt per meter Kelvin, and this is reassuring because the constant temperature boundary condition is used in most modeling today, I think. But maybe this should be this effect should be accounted for if you simulate really short boreholes, for instance, or maybe energy piles, because your biot number then will become smaller. Yes, and we proposed this. Well, the fact that if you look here, I mean, the lower the convection coefficient, the higher the thermal response, and this effect was proposed as a potential explanation for an error that was noticed in the previous similar study. So authors that actually build a lab scale experiment with one borehole and perform some tests and compare it to analytical solutions. And what they noticed is that their experimental data had some systematically higher value than the analytical one. And when reproducing their test numerically, accounting for the convection coefficient at the top, then we obtain a fairly good match with their experimental data. So I don't think this is the only reason for the observed discrepancy, but at least it could be one of the contribution of this observation. These are just some pictures of the physical implementation, which I have to skip fast. I'm sorry. We can go back to the. We could go back to the question time. Now, high temperature storage. So borehole thermal energy storage. And before I dive into it, I just want to say quickly why I think this is interesting. And what we're looking at here, namely, is the total amount of energy consumed in the world and the amount of this energy that is being used in services. And this is the amount of heat that is being wasted. So in the sense that it's not used for any service. And this is really big. In fact, it's more than 50% of the primary energy consumption. Most of it is wasted at low temperature, which doesn't mean that it's useless, but for some application, at least, I think there is a potential of retrieving this heat and using it for better purpose. And especially for electricity generation, we see that this low waste heat component is large. Yes. So I changed a little bit the order of the papers. I am going to talk about paper 7 before paper 6, but in this paper we investigated a case study. So how can high temperature borehole energy storage be combined with combine a heat power plant? And this plant especially was having excess heat production during the summer. It's incinerating waste. By the way, I didn't say that, but when I say high temperature borehole thermal energy storage, it's not, well, the range of temperature we're talking about, I think it's about 40 to 90 degrees maybe. So it's not that high maybe in comparison to other applications, but it's high in comparison to the traditional use of borehole thermal energy storage in ground source heat pump systems. As I said, I think there is a good potential for this technology worldwide, so I think it's worth investigating, and not least because you can perform seasonal storage. So for instance, shifting solar heat from summer to winter, and or this excess heat that we're talking about. This is the layout of the system that we were investigating. So there was a combined heat and power plant, a district heating system, and a high temperature borehole thermal energy storage. And this part is what we model using the software Transys. So the storage itself with some heat exchanger and heat pumps for the heat extraction. This is what the model looks like. We're not gonna go through it, but this is just an example of the type of results that you obtain with the model. So what we see here is the amount of charged energy per year. So these are the first 10 years of operation, as well as the discharge energy from the storage. The mean discharge temperature, and what I call here, or what we call here storage efficiency. I will get back to that later. But for different parameters, and so we did a small parametric study, and it is not a small borehole field, by the way. It's about 1,300 boreholes, 300-meter depth, and with coaxial collector. But the amount of heat that can be charged and discharged is not so different between the case tried, at least. And you see that at the end, at least, of the 10 years of operation, we can charge about 110 gigawatt hour and retrieve 90 gigawatt hour per year. And this is done with heat pump, I should specify. And to get an order of comparison in Sweden, if we look at the residential and services sector, we are about 150 terawatt hour per year. So this is not so big, but it's not so small either. Yes, I mentioned before the storage efficiency, and what we mean here by storage efficiency is the amount of charged, the amount of discharged energy compared to the amount of charged energy. But this is not really, I don't think we could fully characterize this as an efficiency, maybe rather as an energy ratio. And this is what we investigated in the next paper, so in which we looked at both energy and Exergy performance indicator for high temperature borehole thermal energy storage. And the question there was, well, what kind of performance indicator should you use? And maybe how should the efficiency of high temperature borehole thermal energy storage be characterized? And the reason for that is that what I call here the energy round trip efficiency, so the ratio between charge and discharge energy, does not give the whole picture. It doesn't say anything about, for instance, the temperature at which this energy is extracted. So for instance, in the previous slide, the energy efficiency was quite high, but we're using a heat pump, so the temperature, the extracted temperature was quite low. I mean, at least the discharge temperature is an important parameter to consider for your system. Yes, this is what we the borehole field configuration that we investigated, and we use temperature and mass flow as an input to the models. Boreholes could be in series or in parallel. And this is some of the results that we obtained, but we propose 4 different performance indicators. So the discharge to charge energy ratio that I mentioned before, also the discharge to charge exergy, which accounts for the temperature at which the energy that you extract, or at which temperature do you extract the energy from the borehole storage. And also the same value, but for the storage, and also since the start of operation of the high temperature borehole thermal energy storage. We tried different cases, and I think this graph was the main result of the study. And what you can try to understand through this graph is the relation between the different components, and maybe what you could improve inside the storage. So for instance, if you have series or parallel coupling, here we see that the circles are for parallel coupling, and the stars are for series coupling. So it seems like the energy the discharge to charge energy ratio is higher for parallel, so that may be a bit unexpected. But still, if you look at the storage efficiency, for instance, then you have higher values for series coupling. Yes. And then last part about future work. So this was the graph that I showed in the beginning, and as much as I would like to continue working in all these 4 areas, I could say, I think for the thesis I will have to limit myself to the first 2 areas. Although I think the lab scale experimental work and the high temperature borehole thermal energy storage are extremely well, I think they're important and interesting, I should say. But looking first at the thermal response test, and going back to this picture of the heat rate per meter, the system, and so on. Something that I would like to include in the thesis is trying to estimate the system, maybe not in terms of a parametric model, but simply using data to try to catch the true behavior of the system. So when you perform TRT analysis, you assume a specific type of model, and this is quite a strong assumption because you don't really know exactly how the heat transfer or how your system behaves. But your data or the data that you have can help you understand how the system truly behaves instead of assuming a model. Something else which is mainly continuing the work on deep boreholes, and especially trying to characterize the uncertainty of those measurements, and investigate further this hint flux inversion and comparison with modeling, as I was maybe mentioning before. Yes, so I would like to thank all the different sponsors and people who have taken interest in the different project and work that I have done. These were the references I used in the presentation, and yes, I would like to thank you for listening to me. And yes.
Thank you, Len, for a nice presentation.
Yeah.
And now I leave the word to Professor Johan Claesson for the opposition part. Professor Claesson.
Okay, thank you. This was a very clear and good presentation, and you have answered a lot of my questions. In particular for this thermal response test, you have this colorful banana shape, and I didn't understand the projections, but you have, as far as I can judge, cleared it to me now. So perhaps you should have something more written about it. I don't know really. I haven't read any data or details. Okay. So let's see then. I think I'll start with the deeper boreholes.
Yes.
These 800 meters, I find it very interesting, very nice figures. You have a figure of the undisturbed when you just circulate heat.
Yes, I can go back to it, I guess.
Yeah.
Yes, it should be here. Yes. So you,
Yeah,
I guess you meant this one.
Yeah, exactly. I think it's extremely interesting. First, you see you have an increase in the gradient.
Yeah.
So that tends, I suppose this means that the thermal conductivity is decreasing. Is that so? Downwards.
Why do you think so? Because the geothermal gradient is changing.
Have a constant heat flux. This heat is generated from radioactive decay, and I suppose all of it are down, deep down, but I don't know really. So that's my question.
Okay, so your first question was if the thermal conductivity was larger below.
Well, you have a larger gradient.
So here, down. So here the gradient seems to be larger than here.
No, it's larger deep down. The gradient of the temperature. So that will mean if the heat flux is constant, it will mean that the thermal conductivity is decreasing. Is that?
I'm not sure. I think it could be. I don't know if this could be due to any surface effect, but this is quite deep down, so I'm not sure. So it might be, as you say, that the thermal conductivity is lower over maybe the first 100 meters, and then more constant over the rest.
Yes, it has tendency to get constant downwards.
Yeah. I don't know. And I think. Oh, sorry.
Yeah. Okay. Continue, please.
No, I thought it was an interesting question with the radioactive decay inside the ground, and I haven't thought about this so much. I've just read that this is one of the mechanisms that generates heat underground, but I think it could be interesting to understand how we can find out how much radioactive decay we have by looking at the undisturbed profile.
I think you can find that in the literature. I have a vague recollection from the 80s of some geological people talking about it. So I think there is quite a lot of knowledge in the field about that, but I forgot it. It was so long ago. Then you have this case when you circulate the water without, so this is the zero load condition, so to speak, zero heat load. And that's quite important because what we said when we started in the late 70s and the beginning of the 80s is that it is essentially the average temperature downwards that you should use as your T naught.
Yeah.
And the average is roughly halfway down. And has that lesson survived the progress of science?
Yeah, again, I'm not sure if I'm able to answer, but I remember we talked about you mentioned this once before to me, but maybe what would be interesting is to understand how fast does this equalization of temperature occur over time, and what I've been. Oh, sorry.
Yeah, one other thing, you have more figures where you have a wider difference between up and downward channel. Do you have a larger times or larger pumping rates? Have you changed that?
Yeah, I can. I don't have it in my presentation, but I can show them. I can try to show them anyway. So this, for instance.
Yeah. Yes.
Yeah.
You have a higher difference, and
yeah, the flow rate is lower.
It is lower, yeah.
Yes.
Because if you increase the flow rate, then they should be pushed together, of course.
Yeah. Yeah.
So and this process is a very special kind of thing. It's a redistribution from the borehole, from the upper to the lower levels. Because you have a difference, so you must get the average value. And I have thought, for example, does this average value change in time?
Well, if you, or you mean without doing anything to the system, or
yeah,
under...
just the circulating, keeping circulating.
Yeah, I wouldn't know. I wouldn't know right now. I would need to look back at the data. But
I have a hunch, as my recollection from the old days when I did this work, that the change will be very small, because there is the region around that you distribute heat from. It's a few meters around the pipe.
Around the borehole.
Yeah, around the borehole. Excuse me. Yes, and it is a step. It is a mean value all the time. So I think it would be very stable. And actually, this is a very important factor, because this is our physical T0.
Yeah. Something that I've been wondering about also, because you asked me the question once before, was how, I mean, we have a geothermal gradient, and when circulating, we tend to equalize temperature inside and a little bit around the boreholes. But would this geothermal gradient affect the boundary condition at the borehole wall, which is used for modeling? Because I think now what happens is that you superpose different temperature model. So, but you assume that they don't influence the boundary conditions is not changed by the conditions from another temperature contribution, I should say.
I know when we did this study about the thermal gradients, and I have my experience is that practically no geologist did ever understand what we were saying about this average.
Okay.
I would say, for example, that they think that the heat partly comes from below. I would say that it is only changing the level, and actually you have this T0 that you get from this experiment. That is the temperature at the ground surface of the circulating with zero heat load. That is, to me, the third most important parameter in the problem. You have the thermal conductivity and the borehole radius, and the third one is this one.
Yeah.
So I think it's very important to emphasize it, and perhaps it should be studied more, because it was a long time ago when I studied this. Okay, so
yeah.
Then another thing is, if you look at the undisturbed temperature, you have this large change just below the ground surface, the first 5-10 meters.
Yes.
And if you look at the projection of the lower values, that is, to me, the mean value at the ground surface, averaged over the year. So that is also relatively important factor for modeling the surface temperature.
So these points. Yeah, okay.
Yes. So that is the mean temperature in my. So that is also very important information, because you get rid of, you have snow and you have ice and freezing and warm and cold and blowing and everything. And the only important part of this for the borehole is this value. Everything else you can skip.
Well, especially for this depth, at least. This will, I mean, the surface effect will have.
Yeah. Okay. Then I have focused quite a lot on your lab scale model.
Yes.
And my question were, but you have more or less answered it. How far have you proceeded in the work of it?
Yes. Well,
you have more or less answered that, but
yeah, I mean, so the two papers that we wrote are about the design methodology. So, but then we started the construction of the lab scale model, and we have most of the elements to finish the construction and start the test. But this hasn't been done. I mean, the project stopped in between, and then there were new projects coming in. So I think it would be very nice, maybe, well, to continue this work, definitely. And it's I mean, there are a couple of challenges when you try to do the real physical implementation. So for instance, something that I don't talk about in the paper is the pressure drop in those small pipes. So you have to, this is also a practical constraint that you have to account for. And since it's several boreholes, I think you should make sure that the flow rate in each borehole loop is the same. Otherwise, you might test something a little bit different than what you would like. So you have to make sure of that as well. And then I mentioned it was an issue in the paper, but the convection at the top, there is some quite high requirement as well. So there is a question on how could this be achieved.
I will come back to the heat transfer coefficient. I have a comment on that, but the original problem, if you have this scale factor of 600, this would mean a 300-meter borehole depth. It seems to me, because the boreholes, if you have 4x4, it is a few stamps size on the top on this square meter. So it's a very close system, and then so it seems to me to be a mission almost impossible.
Yeah,
do you say?
So you mean that the spacing between the borehole would be extremely small?
Yeah, if you have this, it's 6 meters between the boreholes in the real case. That means 1 centimeter in the lab scale.
Yeah. Now, and that's why. So in the first paper we only studied one specific spacing, but in the more recent one we studied a larger spacing, because I think this could be a problem, that the boreholes are very close to each other inside the test bench. And then you could think about maybe having a small structure like a pipe to emulate your boreholes. But of course there are other challenges with that, because it creates, it's not present in reality. So you have to understand how this would affect the thermal response. If I understood your question correctly.
Yeah, I mean, this is so extreme a kind of world. If you have a 300-meter borehole, the scale of 300 meters, you have the scale of 10 meters between the borehole regions, and you have the scale of 1 decimeter for the borehole radius. That you have said that very clearly. That
if I may add something, because, well, the borehole of 300 meters was the starting point when we thought about this project. But once you have your lab scale experiment, you could upscale it to the real scale borehole field that you would like, let's say. So you might as well simulate a 100-meter borehole.
Of course. Yeah. And I think it's advisable for you to increase the distance between the boreholes also in order to get sort of fine-tuned things.
And there is another benefit of that, which is that the temperature inside the test rig will be lower, especially close to the boreholes.
Then if we talk again, you have a lot of studies of this surface coefficient. And if we take a look at an equivalent size of soil instead, to get a physical meaning of this, then you have that this 10, the transfer coefficient was something 10. And it would be, if you take a lambda of the soil divided by some equivalent length, then you would get a few decimeters. So the heat transfer coefficient corresponds to a layer of soil with some 3 decimeter or so. Do you follow me?
I'm not sure. So you mean for a given Biot number, or are you just?
Yeah. If you shall have 10 and you have a lambda of 3.5, then if you take 0.35 as an equivalent thickness of soil, then it will be the same heat transfer coefficient. So the heat transfer means that you put a layer of 3 decimeter of soil, but you don't have a capacity in it. So it's just a resistance, so to speak. So it's compensated.
Yeah.
But the point is that, physically speaking, this is 3 decimeters. When you compare it, you have 5 meters down to the active, where the ground water surface is, where you have the active length of the borehole starts. So that's 5 meters compared to 3 decimeters. And then you have this size of 10 meters between the boreholes, and you have the size of 100 meter down in the borehole. So to me, the constant temperature should be the obvious choice.
But in I think in your analysis, you have assumed that the Biot number is equal to 1, if I understood correctly.
No, I took 10. 10.
For
10 is
for the Biot number.
Yeah.
Okay.
This is 10, and if you take lambda over an equivalent lambda of soil is 3.5.
Yeah. And
then if you take soil thickness of 3.35 meters, you get the factor 10. So the equivalent thickness of this surface coefficient is 3 decimeter of soil. That's my point, physically speaking, so to speak.
Yeah.
And actually, in many cases, you mostly, for example, so if to this bio number, you have infinite, and then you have this 857.
Yes.
That should correspond to 3 decimeter of soil. It would give the same resistance as this heat transfer coefficient.
Well, if the Biot number is 857 and your real convection coefficient at the top of your borehole is 10, for a thermal conductivity of 3, then the equivalent layer is 300, around 300.
Yeah, 300 doesn't matter, but this means that when you increase that by a factor of 1,000, you have 300 meters of soil as a surface coefficient. It is. I was very surprised. You can think about this, but in my, as far as I can judge,
yeah,
what you say in the lowest case would be low 1, 0.8 something. That corresponds to the resistance of a layer of 300 meters of soil. So it's completely out of any reality. This is the other way to look, but you can think about it.
But I think I didn't really fully answer your question, but I'm not sure I understood. But if I may just, I mean, since we have the graph here, what we see here is,
if you take the tool on the top curve, the black curve, and then the first one, or the infinite compared to the 800 case, they are very close.
Yes.
And this is when you increase. This is 3 decimeters to me. And of course, if you took a constant temperature, or you put 3 decimeters of soil and then put a constant temperature, it wouldn't matter. So it fits with your calculations. So these are correct. But it's only that. My point is that these lower ones are not.
No. Okay, but let me explain why I choose these lower ones, because these lower ones are completely unrealistic in a real case. There is no question. But if you make a lab scale experiment and you let your surface being subject to natural convection, so then you will have in the lab a convection coefficient of around 10, let's say. In the real scale case, this corresponds to a very, very, very small convection coefficient because of the scaling of the Biot number. So that the simulation using this Biot number were just to understand how much could this convection coefficient at the top of your lab scale influence your response.
Okay, yeah, that's fair enough.
Okay,
but I would put cooled controlled water table on the top instead. But then one other thing here: if you have this 300 meters of borehole length, what is this TS? I get it to about 200 years. Could that be correct?
Yeah, I think it was even. I think it's even higher.
Perhaps, yeah.
It's really long. It's really long. Yes.
This means that what happens out here isn't something that it will never happen in reality in the design process.
Yeah, I think that's a fair point. So since, I mean, if you try to emulate in the lab a really deep borehole, then maybe you don't need to go that far into time, let's say.
Yeah.
So
because let's say if you have -3, that would correspond, if it's 200 years there, -3 would correspond to 10 years, and -6 to half a year.
Maybe.
So and I got -12 corresponds to half a day. So my question is a little, isn't the interesting part a few powers below -12 there, and the upper part is not of any.
No, I think that's completely a fair point, because what you would like to do is to validate the models over the lifetime of the installation. So I mean, I would say at least 20-25 years. But again, that's for a 300-meter borehole. So if you want to extrapolate this to a shorter borehole, then you need to look further into the time axis.
Yes, that's a completely different.
But I think it's a fair point, because it would, I mean, it would ease the experimental setup a lot if you just do as you say and don't go as long in time as I did during the simulation, because this would be enough for the model validation of deep boreholes. And then maybe in a second test campaign, if there will be test campaigns, but in the second test campaign you could try to go further in time and maybe address this problem that you see here.
I remember now when we developed this in the 80s, these response functions.
Yeah.
If you have a borehole of 10 meters, you have 20 years. So the latter part is not very important from a practical point of view. And perhaps this would have been emphasized a little more. And then you have 300 meters, and suddenly nothing below zero is of any interest, above zero here on the T scale.
No, I agree. I think it's a good point.
Okay. Then I continue with the thermal response test, and I should perhaps also emphasize that I have not followed this field during the last 30 years.
Okay.
So I'm no expert, but the references that you gave were very extensive, so they are very good, and I will give you credit for that these are very carefully done, and there's a lot of things to learn as far as I can judge, but I am myself no expert in that.
Yeah. Well, a little bit anyway.
Yeah. Then if we go to thermal response tests, paper 2.
Yes.
You used our radial model, Sakib's and my model for the response functions.
That's
and there
correct.
you have these networks in the Laplace transform, and you have Bessel functions and everything. Did you have difficulties to program it, or was it straightforward?
Yeah, so I didn't program it. My co-author, or the main author of the paper, programmed your model.
Okay. But it did work out without trouble, because it's.
Yeah, I think he was. I mean, maybe Alberto can mention it later, but no, I think it wasn't such a problem. I think maybe what was hard was to understand the process of solving the differential equation through the Laplace domain.
Yeah. It was, to me, it was a new thing when I did it.
Yeah.
At that time.
I must admit, I haven't spent so much time looking into it, but we discussed it a little bit with Alberto, who is more expert than me on this part.
Okay. Let's see. And then paper 6, you have this Exergy measurements, Exergy measures. And do you have much use of it? Is it? I haven't read all details or too many details in your thesis, but
yeah, no, I went way too quick during the presentation, but maybe I can show. In order to understand why we thought about this, I can try to show this figure, because, well, The starting point of the Exergy paper was looking at this energy ratio, charge to discharge, and then trying to understand if this was good or not for the system. And he was not telling anything about the temperature at which you discharge. So sometimes you may have a really high energy ratio, but it's not the best thing that you should do. Or you don't have a way to compare it with another system in which you have lower energy ratio, but maybe a higher temperature. So this is what I show here. I mean, here you have two borehole thermal energy storage, and I mean here you charge them with at the same temperature and with the same amount of energy. But in one case you get a lower amount of energy at a higher temperature, and here you get more energy but at a lower temperature. So what is the best solution, or is there a best solution? If you just look at the energy ratio, then this is the storage that is most, but that is best. But also your discharge temperature is lower. So what does that imply for the rest of the system? So I think that was the starting point of the Exergy paper, and using Exergy as a performance indicator. And I should say as a complementary performance indicator, because it's still important, of course, to look at the energy ratio in and out. But I think that in addition to that, you should also look at the temperature that you get out of your system. And then we chose to look at the Exergy, which accounts for this parameter.
So it is a valuable tool then, I guess.
Yes. Oh, well, I think so. I think the main challenge is that until you start using it and understanding how it changes with different parameters, I think maybe it is a bit hard to interpret it in the beginning. But as you test, I think, different or as you apply to different storage, understand what are the causal factors, then I think it becomes even more relevant.
Yeah. I think I agree with you. Do you plan to write an overview, a kappa, as we say in Swedish?
Yes. It's going to be a kappa, I think, yes.
Yeah, because one thing that I miss is what is your contribution and the other authors' contributions. I think that should be stated in some way.
I think that's true, because in the papers I presented, there are a couple of them where I'm not the main author. So I think maybe I should have provided a contribution statement. But
to the kappa, you should do that, I think.
Yeah. No, but definitely. But I can say that, I mean, there are other papers that I didn't include in this work, in which I think I contributed less. But well, I consider that I contributed to I don't know, to a significant extent to the paper where I'm not main author, I would say so.
No. The only thing I think that you should state roughly who did what.
Yes.
I think I've come to the end now of my opposition or discussion, and my general opinion. I got a very good impression. It's a good.
Thank you.
And obviously, I've worked quite a lot with things. You cover many aspects and questions. And this literature survey is, to my knowledge, was very useful for me anyhow. Okay.
Thank you very much
for your work.
Thank you, Professor Claesson and Willem, for a nice discussion. And now we open the floor for the public, general public, for questions. If many people would like to talk at the same time, I ask you to please send a quick message in the chat or raise your hand, and we will try to lead who has the next question. Otherwise, please feel free to jump in first to come. And don't forget to start your microphones in such case.
I think Marco wanted to ask you a question. Marco Fossa.
Yeah.
Hello, Marco.
Good morning, everybody from Italy. I hope all is well there in Sweden and around the world. We are safe and sound, fortunately, here, at least my family and most of my colleagues at the university. Yes, I've really, okay, thank you so much for inviting me to this very nice and very valuable presentation. It was also an occasion for meeting you all, and it is always a pleasure for me to see you and Professor Claesson, Bjorn, Jose, Alberto, and Per, and so on. Okay, yes, I would have some questions and comments regarding this very huge and comprehensive presentation on borehole performance. And I will also paste my comments and questions in the chat, so in case for being more clear. And the first part, or the first question and comment, is related to the first part of your investigation, say on the parameter estimation. So when there are a couple of questions. One is related to the analysis of the effects of applying some noise to the measurements and to the operating conditions. So if I'm right, if the noise you applied is a sort of, let's say, white noise to temperature, or white noise to heat transfer rate. Am I right?
Yeah, this is correct. So in this derivation that I show on the screen right now, there is no assumption about the distribution of the noise, but the noise should be identically and well, IID, I forgot the abbreviation now, but and they have zero mean and the variance that you see on the equation here.
Yes, okay. According to me, since this is a very interesting investigation, it's a very interesting approach to the problem, say parameter estimation and for borehole performance, it would be interesting in a future work, for example, to take into account that the variation of temperatures and heat transfer rate are typically strictly related, and they have a typical period, which is the daily period, due to the insolation effects, the voltage fluctuations that are present on the electric network if you are using an electric TRT machine. So, and this could affect more the parameter estimation if you apply a noise with a main frequency related to a period of a day. And this is a comment of mine.
Yeah.
And another comment, and maybe for a future work or for further comments, is related to parameter estimation and the borehole length, borehole depth. Say you have demonstrated that you are able to get the correct ground conductivity with the parameter estimation, but I mean, I didn't understand. I didn't get which was the typical length of the boreholes you have investigated in such a case of parameter estimation. Probably they are, let's say, short boreholes, typically length 100 of a couple of 100 meters. And probably if you would apply the same analysis to deep boreholes, you would not get the correct conductivity as you have got with the short boreholes. This is a comment of my feeling.
Yeah.
This is not only a feeling, you know, that we are working together
Yes.
on the analysis of deep boreholes. So it is more than a feeling. It is following our discussions.
Yeah, but in this
and,
work, oh,
yes.
sorry. No, I mean, in this work there is no borehole depth. I mean, this is the model that is used, and since the heat rate is already per meter, then you remove this parameter from the model, let's say. So it's the results are not depth dependent.
Yes, I mean, yeah, I understand, but I mean, the temperature profile in time and in space as well depends on the borehole depth. As we know, for example, if the borehole is very deep, you can cross with the fluid temperature the undisturbed ground temperature, and in such a way you can have reverse heat transfer rates, for example, and things that you have shown. In this sense, the temperature profile is deep dependent.
Yeah. Yeah, no, I see what you mean. I mean, now maybe it's hard to relate it with this work, which is rather theoretical, but I guess this would boils down into what model you use for your TRT interpretation. So maybe when you do TRT in deep boreholes, you should have a model that can account for these effects, especially since TRT, well, they're long tests, but they're not so long. So maybe there are some effects of the geothermal gradient visible during the TRTs. I'm not sure if that answers your question, but
yes, was a comment, and also wanted a comment from yours, and also yes, regarding the deep borehole experiments and analysis, this is a to me very interesting part of your work. I mean, you know that I believe that there is a need in recast TRT measurements to take into account the in K ground estimation, because it is a parameter, the geothermal gradient, that affects a lot the K ground estimation.
Yeah. So the sound was broke off a little bit. So you said that we should take into account the geothermal gradient in the parameter estimation.
In K ground estimation for deep borehole.
Yeah.
And another comment, the final comment, I mean, and question, it is related to your box for simulating a borehole field.
Yes.
Yes, and I didn't understand, and I don't remember, because I was present in Stockholm when you presented the 2018 paper. And you are planning to fill the box by sand or other material?
Yeah, it's gonna be sand, and it has to be saturated sand. So yes, that's the plan, because you're mainly because you're more flexible in how you can place the boreholes, for instance.
Okay.
So it's a
yes. since we are planning for another purpose to build something similar, because we wanted to test on a smaller scale some let's say special configuration U pipes. For example, we are planning to use a block of rock cut according to the size and shape we need. And since I've investigated this type of technological problem, and I've discovered that it's not that complicated to ask some people to hydro cut any shape of rock. This could be interesting instead of using sand, where the conductivity is which conductivity can change with the position of your sand volume. So I mean, I would suggest to take into account also to use a block of rock. For example, we have some slate rocks in Italy, which are very isotropic in properties and grain structure inside. So you are quite sure that you can be quite sure that the conductivity does not change from point to point. And also on a rock block, you can apply some precise drilling for locate your tiny heat exchangers.
Okay, I mean, maybe I'm not sure because I don't really know this, but maybe one challenge is to place the temperature probes if you want to have them somewhere else than the inside the borehole or at the borehole wall. But at the same time, I mean, I see that this could. I mean, I hear and I think this could be interesting because saturated sand, for instance, it's from what I know, I think it's quite. It could be tricky because you have some temperature dependency of the thermal conductivity that may be higher than for dry rock, for instance, and water may evaporate through the top surface. So
yeah, this is the problem of using sand. I mean, it is uneven material.
Thank you for the suggestion.
Yeah, and so we have made some investigation about using a block of rock cut on shape, and it is possible with I mean, if we talk about a side block as you are planning to use, more or less.
Yeah.
Okay, and another comment regarding the let's say the sand block. I mean, if I'm right, you are planning to use the 3 borehole arrangement as in a paper by Jose and Patricia of some years ago, where you simulated with the console some copper. Fully copper heat exchangers.
Yeah.
Yes.
We're using this highly conductive material trick, I should say, to ensure that the
exactly. And in this interesting work, it was demonstrated that you can get a temperature response factor, say the correct G function, the one developed with the constant temperature boundary condition, with such an approach. According to me, since you have demonstrated that a copper bar and copper heat source can behave like G function sources, you could also think to use them in your experimental setup, or together with those tiny capillary tube pipes.
I thought,
Okay, that's it.
no, I mean, I thought about it, but I think I mean, this would simplify a lot some practical aspects, but I think there's some interesting aspect to test, like by having U pipes, and I'm thinking especially about some paper linking the thermal response inside the ground to the heat transfer inside the borehole. I think there's one paper by Professor Cimino on that, and in this paper it shows that what happens inside the borehole affects the overall response. So I think for this reason, I think it would be interesting to have the U pipes and being able to test different flows, for instance. But yeah, I thought about what you said for the using some metal highly conductive metal rods in order to simulate the boreholes. But yeah, I also see some practical challenges with that. But yeah.
Yeah, because of the practical challenges of using capillary tubes and exactly measure, for example, the inner diameter according to which you are evaluating Nusselt, Biot, and so on. So I mean, it could be very challenging to work with the tiny dimensions of pipes.
Yeah,
because
no.
at the very end, there is the risk of having an uncertainty on parameters, say Nusselt, Biot, and so on, because you have an uncertainty on dimensions, and for example, uncertainty on diameters.
Yeah.
Anyway, it is very also this part is very interesting, and it's a great challenge. I'm very interested in watching the first results on that. So to compliment again for this part too.
Thank you. It's good to hear. I said though I will not include it in my thesis, but maybe we will be able to pursue the work somehow later on. But yeah.
Okay.
Thank you, Marco. Jose, I think you have to unmute yourself.
Yes, sorry. Any other questions from the audience? We still have 39 participants online.
That's nice.
Raising your hand.
I mean, if people have some questions that they want to ask later on, they can always email me or email you, Jose. So
yeah,
I mean, I'm happy to answer any question now. But
well, if no more questions, I would like to, on behalf of KTH, say thank you to you, Willem, for a nice presentation, and to Professor Claesson for a nice opposition. It has been a very nice seminar, and we thank all the participants as well for attending the seminar. Professor Palm and Dr. Lass, would you like to say some words as well before we close?
I don't have very much to add. I think we had a very good seminar. I like the presentation you gave, Willem. It was we did the test presentation the other day, and I think it was better today than
there were some improvements. Okay, that's good.
Yeah, and so that could perhaps it was because the last time you knew that your audience knew everything you were presenting. So I think it was good, and it was also good to hear the discussion with Johan Claesson. One small question perhaps to Johan would be that do you have some recommendations in which direction Willem should be working if is there something you would like to see in the final PhD thesis?
I think first thing is obviously this laboratory test needs a lot of thinking because of the complexity of the things, but we have discussed that. And the other thing is perhaps this field to try to look at the geothermal gradient and the distribution from that. That should be interesting to dig further in that, I think. So that's my 2 comments.
Okay, thank you very much. I also think the deep borehole and the temperature profile there is quite interesting, and there is more to do, I think, in that area. I think that's all I had to say. Thank you all.
Thank you, Björn. Very good. So I declare the seminar closed now.